So, good morning, everybody, or actually, good afternoon. Hope everything's going well for you all. We're going to start today with just doing a lecture, and I'm going to do this via Zoom, so hopefully you'll be able to watch this later on. All right, so let's go ahead and get started. I'm going to share my screen with you and try to do this through typing onto PowerPoint, so excuse some of the issues that might arise with this as well. Here we go. All right, so today's goal and today's lecture is mainly about thinking about watersheds, watershed delineation, which is going to be your homework 4, and really trying to begin to understand how we quantify some of the surface water components to our water budget. How do we come up with discharge? How do we think about things like overland flow? So we're going to start to go through some of the components of the surface water dynamics. We'll do that today and over the next couple of days. And then we will start to begin to look into more along the lines of the groundwater components. But before we get started, I just want to remind you that on Thursday you have your 2 slides that we need to be taking a look at, where you're going to share them about your water budget project. And for those slides, just one second, I'll be back. So for those slides, what you're going to need is to make sure that you hit all of the components that you need to have. So making sure that you have your watershed location, making sure that you have your watershed boundaries so we know where it starts and stops. In introducing what kind of stations you're going to use to have your water budget, what types of vegetation are in that environment, what's the range in elevations, what's the underlying geology. So it kind of gives you this idea or this sense that you're going to be presenting that, you know, what your general watershed is like and kind of where you're going to get all of your data from. So that will be due this Thursday online. We'll be sharing it through PowerPoint, through Zoom at the time of class. So that's the goal with that. All right. So our next one is what are some of our goals for today? So the goals for today to 2018. So our goals are, one, that you'll be able to, so students will be able to delineate watershed boundaries. Quantify surface runoff in a watershed, and explain the factors that control a stream's hydrograph. And when we talk about hydrograph is a graph, just to be clear right now, that demonstrates or depicts stream discharge over time. And so usually when we're looking at these hydrographs, what we're looking at is increases and decreases in discharge. And typically, right, increases in discharge are being driven by precipitation or snow water melt or irrigation, where conversely, you know, drier conditions are going to cause discharge to decline, or pumping is going to cause discharge decline. So those are some of the things that play a role in that. So let's first go ahead and start to define what a watershed is. So let's go ahead over here. So a watershed is an area of land where all water drains to a low spot. We call that the outlet. And we don't necessarily think of this as one specific point, but it's more like a cross section. So if we were to take a look at this diagram over here and we were to try to draw in and see if I can get something that will just allow me to draw. I'm not sure if there is anything like this, but we'll see. So here we go. If we take this and we this is our watershed boundary here. We can keep going, something along these lines. And we have another watershed boundary that's kind of over here. Those are our watershed boundaries in this system. And then when we go across this, and let's go ahead and turn that line to red so we can actually see it. So these are our watershed boundaries on either side here. And our cross-sectional area, we'll make that orange when we get started, is the area kind of that goes between here and here. So you can kind of see it outlined by these orange ones. We can take a look at it here with this one. But it's this area that kind of goes along here, this being the outlet in this environment. So let's make this orange and see if we can make it really big. Here we go. Right, so our watershed boundaries, right, is kind of this area. Everything that's in here, right, any drop of water that falls within here is flowing down towards this stream. We call this area that divides the system the watershed divide, and so if water falls on this side as rainfall, it's going to come down to the stream over here, but if it's to fall over here, it's going to go down into another watershed. And then we think about that again, that outlet is not just where the stream is discharging, but as you'll find out and as we go through this class, we also consider this entire boundary here because you can have groundwater flow that happens below the ground as well. So it's important to take that into consideration. Now, when we start to think about this, all watersheds can be either big or small, right? So they can be really, really big or really small. So if we think of something that's really, really big, and we can think of the watershed that is the Mississippi watershed. If we think of something really, really small, that could be something as small as the small watersheds at the Conser Prairie. Some of those are only about 100 hectares in size, so pretty small types of systems. 100 hectares is equal to 1 hectare, just so we say this. 1 hectare is equal to about 10,000 meters squared. Okay. So when we delineate watersheds, which is what you'll be doing in your homework this afternoon. So when we delineate watersheds, the goal is to think about what is all of the area contributing to the outlet. And we are able to do this by a couple of ways. So one of the ways that we do this is by specifically having to kind of use contour maps or areas of elevation. So we look at the contour maps and the boundaries and we identify the highest points that are in that area. And water is going to fall perpendicular to those contours. So we're able to kind of draw that water out in that system, draw those lines out in that manner. So what we want to do is take a contour map. We want to identify the highest points surrounding maybe our stream of interest. And once we've identified these points, we then want to go ahead and connect them so that we have an idea, right? So we kind of create, we connect them. And then, and that gives us our watershed boundary. And then we want to follow the contours perpendicular to the contours, and that's going to be our general kind of flow over that we'll kind of think about in terms of topographic controls on flow. So then follow the follow perpendicular to the contours to identify flow path. Now it's important when you're doing this that let's make an added on before we get even started with taking a contour map. We identify the highest points. Before that, we also need to identify the outlet. So let's say we'll take our contour map, our step 1, that might be easier, identify the outlet. Our step 2 is to identify the highest points surrounding the stream of interest and connect those points, which gives us our watershed boundary. And then our step 3 is then to follow the lines perpendicular. There we go. To the contours. Okay. Now, when we're thinking about all the water that drains to off of any given watershed, a small watershed or a big watershed, we can kind of think about those components in terms of their speed at which they go. So we can have several different components that are contributing. So we can think of rivers and streams delivering water at almost one of the fastest rates, and that's because once water is channelized in a river or a stream, it has less frictional force, and oftentimes, right, then we're having a lot of we can have a lot of flow that happens in extremely fast manners. We can also have something that's called overland flow. Sometimes this is also called sheet flow, but it's defined as having water running on the surface of land toward a stream. You can kind of see that over here. We have this overland flow that's taking place in the system, according to this depiction to your right. And then finally, when we think about kind of surface components of runoff, our last one is called interflow. And the reason we consider interflow a surface component as opposed to a groundwater component is that the subsurface doesn't need to be completely saturated for the system to take place. It can just be units of saturation. So its interflow is that flow of water in the subsurface between layers oftentimes, or through macropores. And it occurs as saturated units in unsaturated kind of media. So what I mean by that is that you have the whole vadosome is not saturated, but remember that's that kind of soil zone, but specific units within it might be, so areas of that discontinuity. And so if we take a look at this, we can kind of say and organize it. We can say over here we have kind of going from faster flow, right, up on here, to much slower flow as we go down here. And this change in flow is a result of things we've already discussed, which are things of such as friction, cohesion, and adhesion that are guiding these differences in the flow rates as you move along through these systems. So it's driven by those factors. Now, let's talk about first quantifying this idea of overland flow. So let me open a new slide. All right. So to quantify overland flow, we use what's called the rationale equation. And the rationale equation is a pretty simple equation where we say Q, which is often a term that we use for discharge. And now this discharge is just the discharge that's occurring over the land. So that's our discharge. And our discharge is oftentimes, remember, in units of feet cubed, meters cubed. So let's go ahead and say, put our units down here. So units are going to be feet cubed, meters cubed. Sometimes you'll see cubic feet per day. Sometimes you also see cubic meters per day. Could be written in all those kinds of terms. But it's a volume type of term that we're dealing with here. And this Q is equal to K, which is our runoff coefficient, I, which is our intensity of the rainfall, and AR, which is the area of the watershed. All right, so this is our runoff coefficient. And our runoff coefficient can range from 0.1-ish to 0.95. And if you look at this, right, so it's K times I times, so I'll put some asterisks in here so we know, times AR, and AR should be small. There we go, there we go. All right. And if we look at this runoff coefficient, either it's kind of like acting as your frictional force that's on there, right? So if we pump this up, right, it means that we have less and less ability for kind of infiltration to take place in a system. It means we have more and more water that's going to be running over the system. So not frictional force, but infiltration ability in that system itself. So, when we think about a system that's a natural system, it will have a pretty low runoff coefficient, so natural systems. Where conversely, if we think about a system that is very asphalt, very city-driven, city landscapes, it's going to have a really high coefficient. Like, for example, right now, this morning, it's raining like heck outside. And we know that sitting here at the University of Kansas, there's going to be a heck of a lot of runoff you're going to be seeing across this campus because a lot of it is paved. All right. So then we have our rainfall intensity over here. And that intensity is going to be given in a rate. So that rate is going to be either centimeters per hour, inches per hour, millimeters per hour. But remember, whatever we use in terms of this, it needs to match what is going on over here. So if we say here it's centimeters per hour, then this would be cubic centimeters. If we say it's inches per hour, then this is inches per hour. So we need to make sure that we're keeping with the same units that are there. And then finally, the AR is the area of the watershed. And again, this should be given in something like meters squared or feet squared. So even without really having to think about a system right now, we can ask ourselves a pretty simple question in this system. How would we expect surface water flow to change between environments where we have pretty natural system, or conversely like a city landscape or an area where we have more paved roads taking over that watershed. And so if we ask that question, we think about it and we say, okay, well, let's just go through one example. And we say, okay, we have two watersheds, they have the same area. So watershed area of 100 or 1,000 meters squared. So it's a pretty small watershed. Okay. And our rainfall intensity is 0.10 meters per hour. Okay, so that's a heck of a lot of rain, but nonetheless, this is just to prove the point. And we take a fully a natural and a cityscape or city landscape and solve for the discharge, that overland flow. And what we'll get is if we're in the if we're in our natural landscape, and we will get a value of 0.1 times 0.1 times 1,000. And if we are in our city landscape, in this instance, we'll have 0.95 times 0.1 times 1,000, right? And so if we think about the differences between these two values, right, that's a pretty significant difference here that we have. So we can say, okay, well, you can see that there's a heck of a lot more runoff happening in our city landscapes compared to our natural landscapes. Oops. So here we have about 10 cubic meters per day. And here we have 95 cubic meters per day. So that's a heck of a lot of difference between the amount of water being delivered to a stream. Now we can also go ahead, so this gives us an idea of the overland flow that's happening in a system, but we can also go ahead and think about stream discharge within and of itself, right? So how much water is flowing through a stream? And we want to understand this because it's a lot of water moving around. The environments are coming through streams themselves. So we can have, again, a discharge, Q, which is equal to velocity times a width times a depth, right? Or you could say, right, velocity times your cross-sectional area, right? As we take a look over here. So let's go ahead and just say again, V equals velocity. That velocity is going to be at some kind of rate, right? So it's some kind of length per time. A length per time is going to be like meters per day. Then you're going to have a width. That's in terms of length, which could be like meters. And then you can have your area or your depth, which again is units of length. So your discharge then, when you put these all together, Q should have units of length cubed, right? So volume per time. So that could be something like meters cubed per day. Now, the thing is that we're often trying to get at this idea of discharge, and we have to use calculations to be able to get there. So one of the things that we oftentimes put into the field are two types of kind of probes or gauges to be able to understand the height of the water within the stream column itself. So one of the ones that we use is what's called a staff gauge, and the other one is called a stilling well. Now, a staff gauge, as you can see right here, is basically like a ruler. So there's our staff gauge. It's like a ruler in the water that tells you the depth of the water above the bottom of the stream. Now this is great if you can go out there. So this is a manual type of system. So you have to go out there and be able to take a look at it. And then unless your job is to go out and sit around and watch staff gauges, that's actually a very challenging type of measurement to do for us to be able to quantify discharge as we are going over or through kinds of different storm events or things of that nature, which is what's moving most of the water around. So what we oftentimes instead rely on is something that's called a stilling well, which is on the left-hand side of this image. And a stilling well is just like a PVC pipe that is out and protecting a pressure transducer. So it's just an area where we have a protected pressure transducer. At a known height in the water column, near the bottom, of course. And all the pressure transducer does is determines, so pressure transducer determines the amount of water sitting above it. And so you can say, okay, well, if I know this area right here, and I'm sitting all the water that's above it, I can again relate that back to a depth because I know the elevation, I know the distance from the bottom that I have here. And I can use the data that comes from this to be able to read kind of a continuous measurement on these. Now, pressure transducers often run about $500 to $2,000. And they require you to go out and download them. So it requires also a computer. So there's trade-offs between these two ones, but this one, the stilling well, in this relationship between the depth of the water and the width and the depth to come up with this discharge is typically done for a number of different areas. Now, clearly, the discharge through a stream is going to depend on where you're located in the stream, right? Because the closer you are to the bottom of the stream, the more frictional force you're going to have or more drag you're going to have on the system. And the closer to the sides of the bank of a stream, you're going to have more drag or more frictional force that's taking place. But as you move towards the center of these streams, right, is where you'll have the least amount of resistance forces. And so your stream water discharge at different places is going to differ. So oftentimes what we do is we actually do what's called a velocity profile of a stream. And we do those velocity profiles over different water level heights to be able to understand what the actual stream discharge is as the water level rises in the stream and as the water level falls. So we do these things that are called velocity transects. And we do them because we want to quantify or we want to characterize the change in velocity as we move across the stream or with the stream's morphology, right? It's actual physical characteristics. Now to do these, what we do is break stream up into kind of representative segments and then measure the velocity of each of those segments. So you can see that here depicted to the right, we see that, jumping around. We see each of these segments here. You see that they've been divided into more representative areas. And then we go ahead and we measure the velocity in each of these areas. So we know that this has a certain length and a certain width and a certain depth, right? So we can solve for the area of each of these boxes. And then we can go ahead and measure the velocity. So we measure the velocity using what's called an acoustic Doppler velocity meter. So an acoustic Doppler velocity meter is also called an ADV. And basically what takes place, you see the acoustic Doppler velocity meter that's over here. They can be configured in many different ways, but the goal is that an acoustic beam is sent out in this manner from the center of it. There's several different prongs on the outside, and as you have a piece of sediment or something floating by, it pings off of that acoustic kind of frequency pings off of the sediment, and as it pings off, it's sent back into multiple directions. And what we can do is tell when it's received at the same level from these different receivers of the acoustic of the ADV. It's moving by, you send these signals, and what we can do is say, okay, we know that it's being sent out here. And as we receive the signal back, it gives us information about the particles that are moving in the water, and therefore gives us information about the velocity at which that water is moving. Now, the next question is, where in the column, in the water column, should we actually sample? Or should we take measurements, velocity measurements? And there's a couple of rules of thumb about where we should take velocity measurements, but we take a look down here at this lower left-hand panel, and this characterizes in general, as you move with distance from above the bed of a stream, how it alters the velocity profile, right? So here within like 1.5 or 0.1 to 0.2 feet, we see that the velocity is actually quite, controlled by that drag force. And so what oftentimes we do is we say, okay, well, what is 60% of the depth of the water column? And if we're going to take only one measurement, we take it at 60% the depth of the water column to reduce the influence of that frictional force on the velocity itself. So let's try another one of these. So if we only one measurement, we go with the rule of thumb of 60% times the depth. And that's where we take it. If we can have two measurements, then what we actually do is characterize it by taking the average of the 20%, the velocity at 20% the depth, and 80%. me see, of. And if we have 3 measurements, then we take the or the average of 25%, 50%, and 75%. Now, the thing I have to tell you is that most of the time when you're doing these, streams are actually, I mean, it sounds like a lot of fun to maybe possibly be sitting in a stream, but it's actually not always the most ideal situation, because oftentimes your high flow situations, especially in northern environments, are when you have rain on snow events that are taking place. And if you have rain on snow events taking place, I can promise you that water is freezing cold, and therefore it's not super fun to be standing in the water doing this. So there are trade-offs for sure. Also, it takes a heck of a lot of time to discretize, as you're moving across one of these, to be able to do it. But nonetheless, it gives you a very good characterization of the system itself, and therefore allows you to really understand and quantify the amount of water moving through a stream at one given point. So I know that oftentimes when I think about this, I oftentimes ask questions, especially when it comes to exams and things of that nature, where, I want you to be able to tell me how you would go about doing something. And so in this instance, right, you have trade-offs with the way that you might decide to quantify discharge. If I said to you, you need to go out and we need to do a fast, easy kinds of measurements to get an idea of what the discharge is, you might just use some kind of measurement depth and quantify a velocity very simply at one point, and calculate the width and the depth of the system, and come up with a discharge. But if I said, well, it's really important that we understand the dynamics of the stream, that we're able to quantify it over time and really characterize the discharge coming through this, you might have to say, well, we go out at different heights, different stages when the water is either high, medium, and low. We do multiple velocity transects. We do multiple measurements in those velocity transects, right? So not just the 60%, but maybe the 20 and the 80, to characterize the velocity moving through this system, so that you get an idea of how to go about doing your best, or doing the best you can to quantify and characterize what's taking place in that system. If I said we have nothing and I don't have an ADV, how might I go about just trying to get an idea of water flow? Oftentimes what we do is just throw like a tennis ball in the water, and with that tennis ball we're just able to understand at least how much that water is flowing, and it gives us an idea at the surface of the system. Now that's going to be an overestimate of what's taking place, but at least we have some idea of kind of the general velocity of that system. All right, so the next part of today is we're going to focus a little bit more on thinking about the types of streams that are out there, and then kind of more stream morphology. So when we think about streams themselves, there are a couple of types of streams that we need to take a look at, and we need to be able to distinguish our stream types to different people based on specifically, what that stream is, because it gives people an idea of what time of year it flows, how important groundwater inputs are to it, which helps us to understand a little bit more about the chemistry of what that stream looks like. So being able to distinguish the stream type helps us to, and helps to provide others with information on the stream. So that's why we care about giving them stream type. So we have 3 different kinds of stream type that we talk about. And these stream types have to do, they characterize, in general, they ask the questions or they answer the questions maybe. Answer questions. 1. Does the stream flow all year? The second question that the answer is, are groundwater inputs present? So that's the two different kinds of questions that these systems answer. So if you have a perennial stream, it's a stream that flows all year. And is connected to the groundwater system. If you have an intermittent system, flow is only for part of the year, but is connected to the groundwater system. And if you have what's called an ephemeral stream, it flows only for part of the year and is not connected to the groundwater system. So we can think about oftentimes, when do we see these different types of streams? Ephemeral streams tend to be dominated by interflow. They're oftentimes occurring in high mountain regions where we're disconnected from the groundwater system. So a lot of headwater streams can oftentimes be ephemeral ones, not all of them, but some of them. Then you can move down into areas where you have a bit more connection with the groundwater system itself. You have more water that's available, you have more area to create base flow in a system, and you can have intermittent streams. So you have water there for parts of the year, oftentimes longer periods than ephemeral streams, and you have that connection to the groundwater system, which allows for those intermittent streams to be present for longer periods of time within the system. And then finally, you have these perennial ones, right? So they're always having some kind of water flowing to that system. They are dependent upon groundwater at certain times of the year, not always. And so you have this different characterization of different types of flow taking place in these systems. Now, when we talk about all of these kinds of flow systems, we can characterize what's called the groundwater, surface water interactions that are taking place. And we'll have more conversations about that as we move on, but we need to have a general idea of what these groundwater, surface water interactions look like. So, and in this instance, we're going to define them based on the stream. And we have three different kinds of characterizations. So we can have a stream that is gaining. So a gaining stream is a stream in which groundwater is flowing into the stream. And so if you look up at panel A in this figure on the right, you'll see these groundwater flow diagrams, and you'll see that groundwater is contributing to this stream. And so if we're in condition A, right, this could be a perennial stream or it could be an intermittent stream at this point in time. It couldn't be an ephemeral stream. That's just not possible because groundwater doesn't flow into ephemeral streams. And so that would be the connection that's happening within this system. So groundwater flows into the stream as a gaining stream. Now, groundwater has kind of it kind of consists typically of the average annual temperature. So it has a pretty stable temperature. Also tends to have a lot of interactions with rocks. And so as that water is moving through through rocks and through sediments, it's interacting with minerals, and so therefore tends to have concentrations of things like sodium and calcium and magnesium. Those concentrations tend to be much higher than they are in surficial waters themselves. And so they also bring kind of nutrients to the streams, is one way of thinking about it. We then can have a losing stream. And any stream can be losing. It doesn't have to be perennial or intermittent or perennial or intermittent. So a losing stream just means that surface water is flowing or flows toward the groundwater. And you can see here in this image, you see that surface. You see these blue diagrams coming from the stream bottom and flowing out into the groundwater system. This zone 3 that's inside B, that's considered a losing stream. And so that's typical. You can find that in perennial streams, and you can find that in intermittent streams. And then you can have also what's called disconnected streams. Now these streams are also losing, but they're losing to an unsaturated zone. And if you're losing to an unsaturated zone, then that is typical of an ephemeral stream. And you can see that here depicted in the bottom in C, where you see this water coming through what's the unsaturated zone up here, and eventually making its way towards the groundwater, creating a small dome and a still groundwater flow away from that system in and of itself. So when you're going to give your presentations as we move forward, when you're going to talk about your systems and you talk about the kind of streams that you have, it's important to understand, are the streams in your system perennial streams? Are they intermittent streams? Are they ephemeral? So easily you can just decide when you look at the discharge data if your streams are likely perennial or intermittent. Either they're going to flow all the time or they're not going to flow all the time. And then ways that you can understand if your system is intermittent or ephemeral is understanding where the water table position is in comparison to the stream positions itself will give you an idea of whether or not your streams are intermittent or ephemeral. Now, we can talk then about, we have to continue on this idea of characterizing our streams, because this gives people an understanding of what's taking place in these systems, right? So, you tell someone if it's a perennial stream, they have this idea, that there's quite a bit of water moving through that system and able to recharge that stream. But we also need to talk about the morphology of these streams themselves. So we have several different types of morphology. And the largest control that occurs on stream morphology is topography. All right. So stream morphology is controlled by topography mainly. There are other factors that play a role, but morphology, the topography of the system plays probably one of the largest roles that we have. All right. So we have streams that are controlled by bedrock. So we'll say bedrock controlled streams. These tend to be deep streams. They are considered straight streams. and the water moves really fast through them. We can then have braided streams. And if you look at this diagram down here and we think about what is a straight stream, these A streams are considered straight streams, where we have a lot of water moving through them, where our gradient, our topographic gradient is, so oftentimes greater than 19% in these systems, or 10%, sorry. So, but most likely greater than 2 to 10%. And if we look in those environments, right, these A's and A pluses at the top, these are really mountain environments that you're going to find these. And then we have braided streams. And these braided streams have kind of lost a little bit of the energy. They tend to be at the slopes of many of, or the kind of the down positions of many of these more straight streams. But they're still high enough in terms of their velocity. So their velocity is high enough to move gravel. But still slower than our bedrock controlled or straight streams. And so you can see they tend to create these like more profiles that are a bit like D in this instance. So you have oftentimes a sediment source, you see this kind of sorting that takes place, creates these kind of islands, these gravel bars that occur in there. Kind of looks like someone braided your hair, that type of look. That is something that results from those that high energy environment. And then finally, you have what's called meandering streams. These tend to be your lowest velocity streams. You see a lot of sediment deposition. And this deposition is being reworked and reworked, and it's creating that kind of S shape or meander cutout, or meander cut bank. Look. And so you can see that in E and even down into G, this kind of meandering back and forth. It's really demonstrated in E though, of these quite sinuous streams that move back and forth, and velocities change, and so you have areas of high velocity that cut the stream out and create erosion, and then you have areas of slow velocities within these streams that allow for the deposition of silt and sand-sized particles within the system itself. So our last kind of characterization when it comes to thinking about specifically defining and talking about what a stream is by giving the stream order of a system. So the stream order of a system is just a classification of the stream itself. So stream order is a classification system. And it's used to understand and relate the relative magnitude of streams for comparison. So pretty simple, right? Nothing too crazy. It's derived from the Horton-Staller number. So you can go ahead and Google that and take a look at what it is for a mathematical tree or of a mathematical tree. And the way it works is that each segment of a stream/river is numbered and the way that you start with numbering is you start with the headwater streams. So those are designated as a 1. And then every time 2 segments, 2 or more, of the same order come together, the number increases. All right, so if we take a look at this one here in this example to the right, what we see is that we have a number of headwater streams. And as these headwater streams come together, each labeled 1 and 1, they come together to form a 2. That's the next order as these limbs come together in terms of a confluence and form the next stream down. We see again here 1 and 1 comes to 2, and on the same diagram down here. Now 2 2s come together and they're going to form a 3. Now, as that 3 is flowing down, if 3 merges with another 1, that's going to continue to say 3 because it hasn't changed. When 2 3s come together, then we're going to create a 4. And again, if another 1 order stream comes into a 4th order stream, it remains a 4th order stream. This 4th order stream won't increase until it hits a second 4th order stream in that system. And so we can determine the minimum number of segments feeding into a stream by solving 2 raised to the C minus 1. And C minus 1 is just the number of segments that you have, or the order that it is. That's the minimum number of segments you need to create a stream like that. So it gives us a really good understanding of that system itself. All right, so that's where we're going to end for today, and I will see you guys on Thursday. Have a wonderful afternoon.